So today we are going to learn about the bitwise operator. So what is meant by an operator? So operator is nothing but like an addition. So if we are using a plus sign, it will add two things and it will give you an addition. Similarly, if you are using a minus sign, it will perform a subtraction. On the similar basis, this plus and minus signs are called as operators. So the operators tells you what kind of operation are going to be performed on your variables. Right now we are going to focus on what are the bitwise operators. Those are available in an embedded C. Even in a C also these operators are available and these are performing the same function. So the first operator is called as an ampersand. So this ampersand is performing AND operation and it is always a bitwise operation. In the next coming slide we will see that. Then we have this single standing line. It performs the logical OR operation. A cap performs an exclusive OR operation, and the tilde is perform a ones complement operation. And then we have a greater than sign. It will have a right shift. Actually this is an arrow which is telling you in what direction you are shifting a data. So it will shift right your data, and we have less than sign. It will shift your data on the left hand side. So these are all bitwise operator, and these are very necessary operators when we are dealing with the single bit of a data or a byte of a data. So let us look at some of the examples in the next slide. So in this slide we are going to know how these bitwise operators are going to work. So here I have taken some hypothetical data. So this is the first we are going to look at the first example, that is a bitwise AND operation. So here you can see that we have the bit pattern, that is 1 0 0 0 0 0 and 1, and after that we have the pattern that is 0 1 1 1 1 1. And now what if I perform an AND operation? So it will go bitwise. So 1 and 1, the result will be 1. Now if you look at the next combination, it is 0 and 1. So according to AND truth table, it will be a 0. After that it will be a 0, and you can go ahead and you can look at the D6 bit. It is 1 and 1, so it will give you the result 1, and at the D7 bit it is 1 and 0, so the result will be a 0. So this is called as a bitwise operation. Even we have studied this bitwise operation in 8085, even we have studied the bit operation in 8051. Well, they are very same. So they are performing just a bit by bit operation. Now the second example that I have taken is for the XOR gate. So here you can see that whenever the bit is different, the output is 1, and when we have the similar bits, the output is 0. So let us go with the D0. Here you can see that it is 1 and 0, so the output is 1. And the next combination also in D1, it is 1 and 0, so the output is 1. So whenever we are having a similar bits, let us at a D4 position, here you can see that it is 1 and 1, so the output is 0. So whenever the bit are different, the output is 1. When the bit are same, the output is 0. Now here the only change is that instead of instruction we are using some symbols. Similarly, the down example is for the OR operation. So here we are just going to follow the OR truth table. So 0 and 1 will be a 1. So either should be a 1, the output will be a 1. 0 and 1 will be a 1. And here at D7 also you can see that 1 and 0, it will be a 1. So whatever the example that we have seen in the 8085 microprocessor, 8051 microcontroller, and we have already known that how this bitwise operator works. On the similar basis in embedded C also, this bitwise operator works on the similar basis. Now we can have a really many application by using these bitwise operators. So let us try to write down few programs in which we are going to generate some of the waveform by using a bitwise operator. Now in this slide we are going to look at how the left shift and right shift operator are going to work. So here I have taken one example that x is equal to 7. So when I say x is equal to 7, its binary value comes at 1 1 1 and the rest will be 0. So that is the value of 7 in the binary. So what if I say x is equal to x and the left shift by 1. So all the bit will be shifted on the left hand side by 1 bit. So here after the less than whatever the value is returned, by those many bits the data will be shifted. So here in the first example I have shifted it by 1 bit. In the next example I have shifted it by 3 bits. So here we can see that the shift will be performed, and it is performed from the left hand side. Now at the bottom I have given you the two examples in which we are shifting the data on the right hand side. So the last but one example will tell you that how to shift it on the right hand side by 1 bit, and the last example will tell you to shift the data by 2 bits. So here we can perform a many manipulation using left shift and right shift, and I have already told you that the left shift and right shift operation can be performed to achieve a multiplication, but it is always used to perform some of the bitwise operation in the case of 8051. So we are having some examples maybe in the next slide. Let us look at those examples to clear our idea. Now here in the next assignment, in assignment number 14, we will have to write down a C program to generate a square wave at port 0 and port 1 with 250 millisecond delay on off timing with logical NOT operation. But here we are going to perform only, we are going to toggle only a port 1 with a 250 millisecond delay. As you know that we have already studied how to make a subroutine which generates an approximate 250 millisecond delay. So that subroutine we are going to use in this case. But to toggle the port, we are going to use a NOT operation, and not like P1 is equal to 0xFF and then delay, and then we have P1 is equal to 0x00, and in between we are calling a delay. So it's really a long and lengthy program. Instead of that, we can compress that program by using a logical NOT operation. So let us look at the program, how we can write down that program. Now let us look at the program. So in this program, you can see that it is a standard program, and we have included one subroutine and MS delay that we have already studied. And within a void main void, you can look at this. P0 is equal to 0xFF. So we are making port 0 as an all bits as a 1 1. P1 is equal to 0xFF. So once again, P1 is also making all the bits 1. Okay. After that, within a while loop, what we are doing is, we are first of all, within the two lines, we are assigning those values. Those are necessary. And within the while loop, we are saying that P0 is equal to tilde P0 semicolon, P1 is equal to tilde, and after that also we are putting a semicolon, and after that we are calling an MS delay. So we have just shortened our code. Now in normal fashion, what will be happen is that we have to complement port 0, then we have to call the delay, then we have to complement port 0, once again we have to call delay, and same thing we have to repeat it for the port 1. But here, by using a NOT operation, we have already shortened this program. Now what I will say is that we have already wrote a program to toggle the port 0 by not using an bitwise operator, by using a simple instructions. You just look at those programs and you just compare this assignment number 14 with the previous assignments, and you will come to know that how these bitwise operators are very handy to write down the program. Now rest of the things are very same. Okay, so here you can see that we have a void MS delay subroutine which generates a 250 millisecond delay. So let us simulate this program and let us check out the output. I'll go to the kill compiler. So let us load it. So in the last lecture we have seen assignment number 8. I'll remove this file, so just close it. And from here you have to remove the file, so I'll say remove this file, yes. And right now we are looking at assignment number 14, so I'll say add existing file to the source group 1, and from the folder that I have given you within a tutorial, from this we are going to choose as assignment number 14, add and close. So here you can see the program. So it is a very standard file, hash include regx51.h, and after that we have wrote down a subroutine. So this subroutine will make a 250 millisecond delay. So how this works, that we have already discussed. After that you can see that I have assigned few values like 0xFF, which is nothing but all ones to the port. Similarly, after that we are going to assign a value of P1, and that is also all ones. So first of all we should have a data, and then we can operate that data. So that is why in this case what we are doing is we are assigning some data, So it will be stored within an internal register of P0 and P1, and after that we are complementing the data. Now one more thing, where this sign is called as a tilde sign, which performs the not like operation. Where is this available? So this is available on your keyboard on the left hand side of key 1. So if you look at the key number 1, numerical key number 1, on the left hand side you can see that there is a tilde sign. So you have to use this sign with the shift operator because it is available on the upper side of the keyboard. So this is about the tilde sign which performs the logical NOT operation, and we are calling it within the super loop. So every time it will complement the bit. So first of all the ports will be 1, right? And after that, in the next cycle it will become a 0. After that, the next cycle it will become 1, and to the next cycle it will become 0. So same happens with the port 1. So we are just toggling the port by using an NOT operation. So that is why first of all we have to assign some values, and then we can perform the operation, and in between we are calling a delay. So let us save this file first, and I'll compile this file so that I should ensure that there are no errors. Okay, so in this program we don't have any errors. So let us try to simulate this program, and this program will give you the same output, but the thing is that we have already reduced the number of lines. So I'll go to debug, start stop debug session. Okay, so I'll remove this timer that we have used in a previous case. I'll remove this, and we require port 1 and we require port 0. So I'll go to the peripherals, IO ports, and port 0. So here is your port 0 and here is your port 1, and right now I'm going to run this program in a stepwise manner so that we should check out the output. So we are going to assign 0xFF and 0xFF. So already these ports are 1 because the microcontroller has been reset. So once it is reset, all the bits are by default 1. Okay, and once it is entered within a while loop, you can see that the changes will be happen. So I'll run this program in a stepwise manner. So here you can see that those are becoming 0, and now it has gone to the delay subroutine. At the bottom here you can see that we have used 3 variables I, j. So those are also changing their values. So at the bottom you can see that we have used z, I, and j. So if I click on the stepwise, the counter is gone incrementing. So it will take a lot of time because we are having 250 millisecond delay. So what I'll do is I will run this program in a continuous manner. So here you can see that these bits are toggling. So this is an alternative way by which we can toggle the port by using an bitwise operator. So I'll reset the CPU and I'll stop the program. Even you can use a logic probe to find out its output, and I will suggest that you should go to the logic analyzer and you should choose port 1 and port 2 and to check out the output. So here the assignment number 14 is ends,